So what are the, I'll just list the nonlinear methods we have seen so far. Generalized additive models. It is just saying that the right hand side can be changed to arbitrary functions of xi's, right? Basically something like sum over alpha I fi of xi. And the left hand side could also be changed using link functions. So there was this notion of link function. So you could, basically I'm saying that left hand side you could do arbitrary transformations of left hand side, like a log of y instead of just y, right? And there was then last class we looked at tree based methods. Tree methods, which essentially were something like sum over some constants in regions times indicator of whether x, capital X belongs to region M. Maybe sum over M is equal to 1 to J regions. Okay. So this was the tree-based methods. I mean, basically, let's say cart. In cart, all you're computing is a constant. For example, in the regression problem, you're just computing a constant, and that you will predict as the number if your input variable belongs to a certain region Rm, essentially. I mean, here you cannot see that it looks like a tree, but the regions are such that you essentially have a tree structure, okay, of the input space. Then we looked at forward stage-wise additive models, and specifically we looked at AdaBoost. And these are all of the form sum over, let's say I is equal to 1 to capital M of, I don't know what I used, let's say beta I times B of X. So these are just individual models now. These can be any set of models. For example, for AdaBoost, we just say these are weak classifiers, which roughly gets better than random, let's say. If it was a classification problem, or if it's a regression problem, think of, let's say, beta I is to be some simple regression functions, like, first prediction could be just based on age, age plus a square, square of age or something like that, for if you're predicting income, let's say, right? Second predictor can be just based on age, on let's say education level or something else, like location and so on. So we just saw how to add, so forward stages additive models, which we looked at last time, essentially add one model at a time. So basically you start with no model, or essentially a constant model, and keep adding one model at a time. And the question is, how do we add a model? Of course, you try to minimize some loss, right? So I want to basically if you want to add the little mth model, I have already added m minus 1 models. Then I'll minimize some loss of yi. Let's say it's a regression problem, times yi with f of m minus 1 of xi plus beta m bm of xi. Okay, final bracket is not going to be visible. Right, you're minimizing over beta m and bm. Okay, basically you've chosen m minus 1 models. Let's say that's the running average so far. You're just adding one more model. So these are additive models. I mean, you can see that there's an additive structure to all these models. So you can always do even regression. You can probably just add one variable at a time, get a beta, and then add one more variable, get another beta, and so on. It may not be the best. You can always try to find all betas at the same time, so all b's at the same time, but we haven't seen that version. Okay. So And then specifically in forward stage-wise additive models, we looked at gradient boosting. As a way to add the mth model in the case when, for example, when models are trees. So these are all nonlinear supervised learning models that I'm talking about, right? So this is what I was trying to cover towards the end of the last lecture, and I will try to recap it because it's in addition to random forest that we're going to look at today, which is also going to be additive. We'll see the pattern. Gradient boosted models, gradient boosting models, are basically gradient boosted trees, are one of the most popular methods that you can use. So there are packages like XGBoost, which are computationally efficient ways to compute the parameters of this particular model. Okay, that you can use in Python or R, and so on. So let me just recap gradient boosting. Has anybody went back home and seen gradient boosting and got confused? No. Okay. So gradient boosting is the idea that first of all, it depends. The idea is about using gradients. So what is a gradient? I just defined last time. So I'm just going to expand this, okay, for now. So idea is to think of gradient. Think of gradient method, and I'm going to explain what the gradient method is. It's quite straightforward. Let's say you had some objective. Okay, let me just use obj as the objective. You had some objective and you had some parameter, which was, in this case, I'm going to write it as h. It's a vector. So let's say it's, let's say h is n dimensional. And you want to minimize over h, all vectors of, some objective. So the idea of gradient method is just to say, okay, can I compute the gradient So the idea of the gradient is just to find the partial derivative objective with respect to, let's say, the h1 coordinate, all the way to partial derivative of objective with respect to h(nth) coordinate, right? This will be the gradient, and sometimes this partial derivative, depends on the current value of h, because objective is a function of the whole vector, right? So this would be n dimensional gradient. So let me actually give an example as well, just to kind of really clarify this. So let's say the objective is actually yi minus hi the whole square, sum over I is equal to 1 to n. Just an example function. I just want to, don't worry about, I wanted to write a function of n h's, so I just wrote this as a function. For this, what would be the gradient? It depends on all the h's, right? So the objective involves all h1 to hn. If you take the gradient with respect to h1, let's say, partial derivative with respect to h1, what would you get? All the terms, there's only one term which involves h1, and that's going to be minus 2 times yi minus h1, right? Sorry, y1 minus h1. So this would be the gradient. So the gradient depends on the current value of h1. So you need to substitute something, right? So typically gradient, and it's just an intuition. If people are more comfortable with gradients, just ignore this, informal definition, informal way of saying things. But basically, you need to evaluate it at some h is equal to some current value, h as in the h vector. So as I said, for example, here the partial derivative of objective, which depends on the h vector with respect to h1, is this. So it depends on h1. It depends on the h vector, in particular only on h1 coordinate of h. So I'm to put numbers here. Let's say y is some data. Okay. There's a number, but this depends on h. So that's why I'm going to put the current value of h. And in particular, among the current value of h, maybe just pick the first coordinate, substitute here, you get a number. That would be the gradient is a vector of numbers. And to make them numbers and not the symbols, because here is a symbol, this part is data. You want to kind of take a gradient at the current value. Okay. Once you get this gradient, then the gradient method just says that there are many variations which are there's backed with guarantees about how long does it take to compute the minima, how long does it take to solve this problem and so on. Let's not worry about that. The gradient method just says let's do something iteratively. We'll start with some iteration h naught. Start with some vector, and then we'll keep on, and then we'll do this. We'll go to the tth iteration, or let's call it t plus 1th iteration. It's going to be whatever value we had at the tth iteration minus some constant. Let me put eta, but just think of this as some constant. Let's say 0.01. Okay, times this gradient. Okay, this is the gradient method. Okay, if you have an optimization problem and you can compute gradients. Okay, so you need to have an objective for which you can compute the gradient with respect to what you're optimizing for, h. If you can do that, then keep computing gradients. Compute the gradient. So this gradient, it may depend on the current value of h, which will be ht. So gradient at ht. Okay. Compute this vector. You have a current vector. Subtract the vector, two different vectors. You get the next vector. Okay. And now with this vector, compute the gradient. Subtract it from ht. You get another vector, and so on. And it turns out that this method roughly works. I have to say something about what is this constant here and so on, but don't worry about it. This constant can be set. There are different ways to set this constant, and gradient boosting. So gradient boosting method kind of uses this fact. Okay, this type of update it uses, and I'm gonna in the next couple of minutes say why or how it uses that fact. Okay. Okay. So gradient boosted methods is basically just trying to find sum of Tm, which has parameters theta m, I guess. I don't remember what notation I used. So, as I said, this is also an additive model. This is an additive model. It's a bunch of addition of trees. Okay, there's no subscript there for trees. There are m trees here, capital M trees. So I wanna, instead of making a prediction in one tree, let's think of this regression tree. I built a tree somehow, okay, using data. Instead of making a prediction in one tree, I wanna instead add many trees. And all the trees, of course, use the same data. Somehow I'm fitting the parameters. You may say, okay, I may get the same again and again. Of course, that's not what we want to do here. And see, so this is a general pattern. So let's compare this with the original pattern, which was here. Additive models generally will have a pattern with some more m models or some coefficient times individual model. Okay, right? But if you see how the way I've written, I've kind of not written a coefficient, right? There is no beta little m here, no coefficient here, but there is an addition of bunch of models. Okay. The reason I did not write the coefficient is, if you remember, for a tree, there is this constant, right? Is the sum of constants and indicator of whether x belongs to that region or that region of the input space. If you explicitly have another coefficient, it's just a multiplication of those constants with this coefficient. So you can just push it into a tree description. Okay, so that's why I don't have explicit coefficients there. Are people following at this point? Because I'm not even told anything about gradient method, but you wanna be sure about what I'm saying so far. After that, maybe things will become a little fuzzy. It's fine. Any questions at this point? Okay. So for this, so in the stage-wise additive modeling, so we said we want to find m such models, but we want to add these models one at a time. So I want, given m minus 1 models already, somehow I fit m minus 1 models. I want to find the mth model. Okay. Right. So how do we find that? You can just, to kind of get intuition, you'll say, okay, maybe I can find the mth model by theta m is the arg min over all theta m's of sum over I is equal to 1 to m. Sorry, not m. Actually, there's a typo in the notes. 1 to n of a loss of yi, comma, m minus 1 models. Let's call this summation f little m minus 1 of x. Okay, I have some or only m minus 1 models. Then it's yi f of m minus 1 of xi plus I'm trying to find the last, the mth model. It's going to be t of xi comma theta m. Right. This, I mean, I've already found m minus 1 models, so those are, they'll make some prediction. Maybe already they're making some prediction, but there's still some error that you want to capture by adding one more model. Okay, essentially, that's the way to think about it. And you want to find the best parameter because there's a tree. All the predictions are linked through this parameter. Once you find the parameter, you can make all the predictions and so on. Right. And last time I said in the trees version of the gradient boosting method, we kind of take note that if we knew, so what is theta? Theta is going to be a bunch of constants, right? C1 to Cj, and a bunch of regions, R1 to Rj. Let's say there are j regions, j leaf nodes. Okay. In the sense, I split the input space into j parts. Then I'll have j constants, right, to make a prediction, and there'll be j parts, j regions. If we know the regions R1 to Rj, okay, then for each region, right, then for each region I can solve this constants. Okay, this constant for, let's say, region little j is equal to arg min over just that constant. Find some constant Cj, let's say. Again, the same sum, I is equal to 1 to n, because since I'm only trying to find the constant of that region, since let's say assume I know the regions, then I'm only trying to find the constant of the region. It's going to be sum over 1 to n of L of sorry, not sum over 1 to n, it's sum over all those data points which belong to region j. Okay, because I'm only trying to find the constant of region j, so that can only affect the points which are falling into that region, right? Of L of yi, all the predictions made by the previous models, plus this constant. If you can find such a c, then that you'll just set that c to be the parameter of your new mth tree. Okay, if you had the regions. Okay. Now, but we don't have the regions, and so there is some nice way. This is the gradient trick. So there's some nice way to kind of look at this problem and say, okay, I'm gonna use gradient method here. Some sort of grade. So we're gonna use same gradient method here, but it's not clear how to use gradient method. We are not gonna do a gradient update with theta m as a parameter. Okay. So you saw previously, gradient method. I just said if you have some objective with respect to some parameter or something that you want to kind of maximize or minimize over, then you find the gradient with respect to this guy and kind of iteratively update. Right? Instead of that, the way we'll do it is, okay, let's say so essentially, even if you figure out a tree, the tree is only going to make n predictions, right? Because I have only n training data points. So let's say the predictions are all, I'm going to call them h1 to hn. Okay, the predictions are h1 to hn, which means that I'm going to say, let's say there was a tree, an example tree, then I'm going to essentially, the tree's performance would be just L of yi comma fm minus 1 of xi plus okay. Let's say hi. Actually, instead of writing it this way, let me even remove this guy and say there's some loss. I mean the same loss as before, and the reason why I removed this term is I'm going to intuit how the term kind of comes back in here. So let's say this whole thing was hi. I mean, of course, in a sense, I have to make n predictions by adding one new tree. But let's say whatever predictions for each of the ith example, let's call it hi. Okay. Right? So now there's no model here at all. Right? I just said there are n numbers as long as I fit. Ideally you want to make those numbers the same as yi's. If you had full flexibility, you just say hi is equal to yi and done. Loss will be 0. Right? But what we'll do is, okay, there's a loss with respect to some parameters. I'm gonna now take a gradient with respect to hi's. Okay. That's going to be an n-dimensional vector. Right? So I can always take the gradient of this guy with respect to, take gradient with respect to hi's, which is going to be, so the gradient is going to be n-dimensional. Let's call it g. Okay, it's going to be n cross 1. And the gradient, okay, let me write one component of it. Let's say g ith term, okay, is going to be equal to the gradient of L. Okay, ith term, the ith coordinate here, there are n terms here, but I only corresponds to one of these terms, which involves just hi. Okay, so we take the gradient of L with respect to yi comma hi with respect to gradient of hi. I'm going to evaluate hi at fm minus 1. Okay, so this gradient may still depend on h, right? Just like an example before, but the h I am going to substitute is all the previous models that I have fixed at the current xi. Xi is zeta, yi is zeta. Fm minus 1 is also previously chosen and fixed model. I'm going to say hi. I'm going to evaluate this gradient at this point. So once I get this gradient vector, now I can say my update essentially is going to be I guess h new, I guess h t plus 1, the vector is going to be equal to h t, which is these guys. That's how I define, if hi is fm minus 1 of xi, then hj is fm minus 1 of xj. That's just make a vector. It's going to be n of them. So I'll just call it ht minus, just like previously I had put an eta, right? Eta or whatever, something like 0.01, let's say, times gradient. Okay. So it's the same as, so this kind of stays like, I had previous m minus 1 models. That's my current situation of how I can make predictions. I'm essentially kind of updating my models. It's essentially the predictions of my mth, my little mth function, my prediction model is just going to be whatever previous m-1 guys predictions they're making over each of the n examples minus eta times the gradient. Okay? The gradient is just from the gradient of the loss with respect to this HIs. So that's the analogy with the simpler example I showed above. So with this you can so here I've removed the modeling part. Right? I just said let's ignore the whole models, just make this HI, which was essentially fm minus 1 of xi at the current value. I want to add one more thing. If you remember, so previously this HI here, or HI of t, okay, I should not use t, maybe m minus 1. Yes. This will use m minus 1. M minus 1 and m. Okay. So in m minus 1 iterations, you already fixed some m minus 1 functions. The predictions of those functions are going to be this n-dimensional vector, right? For each one for each example. And we want to add one more function. If I added one more function, functions predictions, then I'll get the predictions by the m functions. Okay. The predictions by the m functions are going to be this. The predictions by the mth function is going to be minus eta times g. Okay. And eta is so mth function's predictions are going to be this. Okay. So now, if I say that the mth function's predictions are going to be minus eta times z, or scaling is not an issue because remember additive models had this beta I times capital little b of I, so that the coefficients are not very critical. I said they can always subsume, especially in tree models, these coefficients, constant numbers can be subsumed into the model. Right? So now, if these are the predictions by the mth model, then I just need to build a tree with these as the predictions. That's all. That's it. So that's gradient boosting for trees. So at this point, so basically you have m-1 models, evaluate the gradient. Right? If the gradient requires information about the m-1th evaluation, then you just substitute it. Okay. Once you get the gradient, just make a tree with g as the predictions, or minus c as the predictions. It's basically the same thing. G vector as the predictions. Okay. So either you use g and x data matrix, or you use minus c and x data matrix. Okay. So this is your x comma y pair. Just build a tree. Okay. When you build a tree, you'll get regions R1 to Rj. Right? You'll get regions as well as you'll also get some constants. But what we'll do is we'll ignore those constants. We'll get these regions, and then we'll go back to our original observation that if we had these regions, where is this? If we have these regions, then for each region I can set the constant. Okay. So that's how I'm finally getting the tree. Although I get the initial tree with making predictions on gradients. Gradients as a prediction as a bias, and my data is just data. I'll build a tree, but I'll only pick the regions. And for each region, I'll again set the coefficient according to this equation. Here everything is constant. This is constant. This is constant. I'm only trying to set this number for the region that I got using the tree I constructed now. And then once I get all these j numbers, I have the j regions. That's then my mth tree. And then I keep repeating this. That's gradient boosting. Okay. It's a slightly clever. So why are we even doing gradient boosting? Because we cannot add a tree. So if we have this, we want to make a sum of trees by adding one tree at a time. We cannot do that using simple, it's very hard to add an additional tree. That's essentially the idea behind gradient boosting. There's really nothing else going on. I mean, it's very difficult to optimize for all trees together anyway, and so we are doing something stage-wise. Even stage-wise, adding a tree is difficult. So we're gonna do this using gradients as information, as a way of as a way of speeding up getting a tree, getting m tree and m plus 1 tree and all the way to maybe some m that you decide, and then you stop. Okay. Any questions about gradient boosting? Yeah.
So in each iteration, are we making the tree better?
We're getting a new tree in each iteration.
So, but it depends on the predictions up till now. So for
It depends on. I mean, when you're building a tree, it depends on what predictions you've made up till now.
yes.
Sorry, not just predictions, but the gradient depends on the current predictions that you made up till now.
Yes.
So it's like analogy to gradient method. What gradient method does is kind of, just in terms of predictions, right? I want to make, at the mth time, I want to make n predictions. At the m minus 1th time, I've already made m minus 1 predictions, and I want to add something. Okay. The analogy is that think of the objective as some sort of a ball, and you're trying to kind of, if you think of just in terms of prediction vectors, h, which is n dimensional. Okay. You're basically starting from some point and trying to go down this ball. Okay, go down like you want to go here. Yeah, to the lowest point. Yeah. So gradients are just helping you figure out the. It's like an additive component. Gradients are the same dimension as the parameter. In this case, the n predictions. So it's basically trying to push you towards minimizing whatever your objective is, which is L of yi comma sum over 1 to n, also 1 to m of all these m models. Any questions? Go down this, actually maybe I should draw it more clearly, a bigger curve. Yeah, it's making you go, I mean any gradient method will try to do this. We just kind of saw the analogy with, ideally want to get whatever be the objective as a function of parameters. Sure, if we're going down, gradient descent. But there's no, I mean, it's a huge family of huge family of variations with the techniques. So how do you choose this something called eta that I was using as, let's say, 0.01? How do you choose that? You can set it to be constant, you can keep changing it and all that. There is a lot of things going on, but this is a family of gradient methods. Wherever you're using gradient information to go down to best optimize your objective. It's related to how far you'll go. No, I mean it's the gradient itself. Here the gradient is steep, here the gradient is not so steep. So it also depends on the magnitude of the gradient. So the each coordinate of g here, if you're on this side, will be high, and so you'll make a bigger step. If you're very close to the bottom, the gradients will be very small. I mean this just just in terms of intuition, but don't worry about it. What is the question? This is the gradient at this point. Okay, this is the definition of gradient. Your question. So gradient is always going to be, you go in the negative direction of the gradient. But I used to be confused about this quite a bit. So the gradient is really, although I draw a slope here, it's not really, although I draw a slope type thing here, in one dimension, what is the gradient? It's just a slope. It's a one number. Why am I drawing it as a line? It's a little bit of so the right way to think about is actually, let's say in 2 dimensions. If you think of a ball, it's going to be some circular thing, right? If you just look at the top of the ball, contour lines. Remember, we were doing this for ridge regression. It will look like a ball, look like these contour lines, and the gradient is just going to be. And your parameter space, let's say, is h1 and h2, let's say 2-dimensional. Then let's say you're at this point, the gradient is going to be like a vector like this, orthogonal to that contour line. The gradient is supposed to be the same dimensionality as your h, the gradient. I just defined the gradient. Right? It's just if h1 and h2, then there's 2 coordinates of the gradient. The gradient is by the way we, by definition, it's going to be just whichever is the lowest point is going to be always opposite in that opposite to the lowest point, always perpendicular to this contour line. Okay? And negative gradient just means go in this direction. Okay, this is the actual gradient. This is just a way to say, maybe this picture is a little bit misleading, but this is also gradient descent. This is also gradient descent or gradient method.
We were thinking that.
Yeah, this is
first because we were thinking we are going like down towards minimum.
You are.
And
here also you're going towards minimum. Let's assume this is a minimum. Like a ball.
Yeah. So the
ball's lowest point I've drawn as I've drawn it as contour lines. Right.
But then this arrow direction is taking us like
That's a gradient and negative gradient. So remember I put a minus eta of gradient is always about if I change, so gradient, intuition of gradient is if I change h1 a little bit, h1 from h1 plus a little bit more, then how much will my function increase? Okay, that's the definition. Definition of each partial derivative. Gradient is just concatenation of each partial derivative. Okay, so that's GBM. Yeah, and now let's look at boosting. Random forest. So random forest really, it's a hand wavy theory. So actually, in the sense, hand wavy at least in this course. But there is some partial explanation that you might not have seen. So today I'm going to cover random forest, also multivariate adaptive regression splines, and then support vector machines. Okay. So how many of these methods have you already seen? Some of you or all of you? 2.
I'm not sure about the math, but
Okay, this is not very difficult. So who has not seen any of these methods? Okay, none of these methods. Okay, what about you? Oh, actually, is everybody's name here? Yeah. Oh. Okay, let me count. 4, 15. Okay. 4, 8, 12, 15. Okay. So Mars is something that you've not seen. So so how much have you seen about random forest? Have you just used it, or maybe you know the description of random forest, but do you know why random forest in the large scheme of things? Sure. But why random forest? And why do you want to decorrelate this? Why does correlation overfit? Huh? Why? All the methods are trying to reduce error anyway.
If you are having the same correlation of the trees, there are 10 trees which are having 10, 9, 8, 7.
Sure.
So the average error would be less compared to 10, 6, 5, 4.
I didn't understand that part. But see, in grain boosted trees, the example that I gave you, there is addition of trees. I'm adding a bunch of trees. I'm not talking about correlation at all there, right? But they are pretty good in terms of performance. So you're trying to say decorrelating trees helps, right? That's roughly what you're trying to say. The question is why, and the answer to that is actually maybe partially covered in, I guess, the second lecture or third lecture when we talked about bias variance trade-off. Okay, so in support vector machines, those who've seen support vector machines, have you already? So you guys said you've already seen support vector machines. So support vector machines, at least in this course, correspond to the kernelized version of the support vector classifier. So you've already seen kernel trick, or no? Not you, but you've already seen kernel trick. Okay, so this is going to be fast. So I'll try to, I mean, I will not give you a very rigorous guarantee of why random forest is a better thing than something else. But I'll do some hand wave explanation here. So maybe you just check whether it aligns with your intuition. Okay, I'm gonna describe that right now. So before random forest, so random forest, I guess, predecessor, or let me just use. There's this method called bagging. Okay. So what is the idea in bagging? Bagging is essentially an acronym for a short form for bootstrap aggregation. And remember we did bootstrap samples, right? If we had a z I don't know if I put star there, we created b copies, z star 1 all the way to z star capital B for some capital B copies, and for each one of them we essentially created a predictor, right? F star 1 of x all the way to f hat star b of x. Right? So from data we sample with replacement every observation. So maybe there's n observations here, and maybe each of these intermediate data snapshots, derived data that we got also has n observations, and then with each observation we build some model. Maybe it's a tree. Okay, let's say it's a tree. So we have capital B trees, and bootstrap aggregation is a straightforward idea which says my final prediction, I've had bootstrap, I guess, bagging of x is just, let's say we are in regression setting, so we created regression tree, then I guess 1 by b sum or little b is equal to 1 to capital B of f hat star little b of x. Okay, so this is my bagging predictor. Okay, so previously we did this, but we are taking we are trying to find confidence bands. Here we are saying let's just take the mean, and that's my prediction. Okay, so let's understand the impact of correlation here. So why is bagging better than just using one tree? That is true. So let's understand that that aspect separately with just random variables now. Okay, so that it's clear why why bagging may make sense. So let's stop at this point and say, okay, let's say I have random variables w1 to w capital B. Okay, these are random variables, and in the first case, let's say they are independent, and let's say they are identically distributed. They are they follow some distribution. Okay, then what is the expectation of sum of I is equal let's say B is equal to 1 to capital B of Wi, let's say 1 by B. What is this expectation? It's just going to be the expectation of any one of them. Okay, so let's say they're distributed according to PW, which has a where the expectation of W is equal to something, let's say W bar. Okay, so mean. Actually, let me just use mu. So this is mu. You should verify that this is mu. In a sense, that just follows from something called linearity of expectation. So expectation of a sum of random variables is the sum of the expectation of these random variables. and each random variable has the same expectation, which is mu. So the numerator is b times mu, and the denominator is b, so you get mu. Okay. So that's expectation. What is the variance of maybe I should put 1 by b inside 1 by b sum over b is equal to 1 to capital B of wi. What is variance? Let's say expectation of w is mu, and variance of w is equal to sigma square. Okay. So what do you think this variance is? Any idea? These are independent random variables. So the variance of independent random variables is going to be the sum of the variances of the individual random variables. Okay. So, but what about this nagging constant here? What is the variance of, let's say I have a random variable whose variance is sigma square. I multiply the random variable by 10. What is its variance? What is the variance of 10 times that random variable? Because of the squaring thing, it's not about intuition. You should just derive it offline, that it's going to be equal to 1 by b square 1 by b square sum over b is equal to 1 to b of sigma square. Okay, and this was just equal to sigma square by b, right? So I said first I pulled out the constant just becomes square of it, so 1 by b becomes 1 by b square, and I said variance of a sum of independent random variables is the sum of the variances. So in each individual variance is sigma square, so there are b of them, so there's numerator is b times sigma square. So anyway, so this corresponds to your intuition that variance decreases if they are independent random variables. Okay. Now let's say so I'll give you another thing. Let's say case dependent random variables. In fact, they're dependent random variables, and in fact, let's say the dependence is exactly so the covariance between w okay, this is not I anyway. WB1 comma WB2 is equal to rho sigma square.
When you say case is dependent, means those trees that have like dependent?
No, here I'm only talking about random variables. Forget about trees here. I'm saying if you had V random variables, the expectation is this, their variance is this. If you have V random variables which are dependent, okay, and specifically what do I mean by dependent? Two random variables, they have a covariance which is non-zero. If it is zero, then if it is zero, you cannot say it's independent. Actually, all the moments have to be zero to make them independent. But anyway, so I'm just saying, dependent in this way. I'm only capturing the second moment essentially. So for this, the variance of the sum, so variance of 1 by b, let's say sum over b is equal to 1 to b of wi. I'll just write down the formula, okay? Because variance is just squares, right? If you remember, it's expectation of square of some difference, right? So you can just you can use basically a simple formula like a plus b plus c minus d the whole square. You can just expand the square, so you'll get multiplication terms. So essentially, this is going to be equal to 1 by b square anyway. That we knew from before. It's going to be sum over b is equal to 1 to b of the variance of each individual guys. Okay, let me just write it. Variance of WB plus 2 times sum over B1 is equal to 1 to B, sum over B2 is equal to 1 to B1 minus 1 of the covariance of WB1 comma WB2. Okay. It's like cross terms, okay. And there's a bracket closing. So what I'm saying is, if you have variance of, so first of all, I got rid of the constant, push it out, and you have sum of, let's say B terms, then you will have individual square terms, and then you'll have pairwise terms essentially, and that pairwise term is essentially a covariance term, and that's why I wrote the formula of covariance for. That's why I wrote down the formula for what I mean by covariance in this setting. So this is again a fact, as in you can expand the squares. Try it for B. Capital B is equal to 2. You will see that this is a formula. Capital B is equal to 2 is just saying that sum of x, two random variables W1 and W2 is just the sum of their variances plus 2 times the 2 times there's no sum here. 1 to 2, as in 2 terms will be there of covariance. 2 times the covariance. Covariance is symmetric anyway. You can derive that. So what I want to show is that so let's say things are dependent. Then I want to just substitute the definitions of what is the variance of WB. I just assume to be sigma square, right? So let me just substitute them. B square of sigma square, and there's sum over B. So this is B sigma square, right? First term is easy. Second term is 2, and there is this double summation. We know that the covariance doesn't depend on B's. Okay, I just assumed it to be that way, right? Covariance doesn't depend on B's. There's B1, B2, but it's a constant for any B1, B2. So I'll just take this out. I have to substitute it here, but it doesn't depend on summation, so I'll take it out. So I'll have 2 times. 2 times rho times sigma square times the summation turns out to be B times B minus 1 by 2. Okay. This summation is basically saying for B1 is equal to 1, there is no counting. For B1 is equal to 2, I'm going to count 1 and 2. For B1 is equal to 3, I'm going to count 1, 2 and 3. So it's like sum of the first 10 numbers many times. Okay. So this is the, I mean, if you don't like that expression, you can just look at, covariance matrix has basically B square entries. We are basically summing up the off diagonal entries, which are one sided off diagonal entries. So this has B square entries, there will be B diagonal entries, and the ones below the diagonal entries, or the ones only above the diagonal entries, will be just this number, because they all add up to B square numbers. Okay. So here you can see that this is equal to sigma square by B plus rho sigma square minus rho sigma square by B. I mean, I just expanded, first of all 2 and 2 cancel, one B term cancels, right? One term involves just rho sigma square. Oh, there's a this is fine. Yeah, rho sigma square. I mean, I could have put the both terms in one. I just separated them out, and you can see here that as you average these B random variables, the variance decreases only through the effect of B, right? But you can see there's a term which is constant, which doesn't depend on B. So if the random variables are highly correlated, which means high rho, this rho value, then the variance doesn't decrease. Okay, it decreases up to some point, in the sense of this guy goes to 0, let's say this guy goes to 0, as in like decreases more and more as you add more and more random variables. But if they have a constant, some correlation, positive correlation, here I've just assumed constant, same correlation across for every pair, then you don't get a decrease in variance. Okay, that's just for random variables. But this intuition carries over to bagging. In bagging, also, if the trees are correlated, okay, in the sense that predictions are correlated, that's what I mean, then you will not have variance decrease. Okay. So that is the main issue with bagging, and that's what random forest is trying to address. So random forest addresses reducing variance, whatever the summed up predictor, right? F hat, so F hat random forest of X. Hopefully this guy's variance is smaller. Okay. Oh, actually, I should, okay, this was not, the last point was not correct. Reducing so addresses reducing correlation between trees, right, while not increasing variance. Okay, so there's this so we are trying to decorrelate trees, right, which means that we are actually increasing variance. Okay. So we are not controlling the variance of the predictor. If you have 10 let's say 10 trees, then the variance has to decrease. But if the things are correlated, then it doesn't decrease, like there's a lower bound. I mean that I didn't show for trees themselves, but I said for random variables you can see how it is. So this is just an example, random variables that we saw. So we want to kind of somehow get rid of this row. So we want to directly attack this row. Okay. But when we are attacking the row, we don't know what's going to happen with the variance of the predictor. But hopefully it doesn't increase. Okay. Ideally you want it to even decrease, but you cannot directly make a connection. Is that clear? So that's the agenda. So we want to decrease correlation, and as you probably have seen in some of you have seen in the other class, so random forests are about doing something with basically making a change for bagging. So change bagging that I just showed earlier, that you create the bootstrap sample and create a tree. But while creating a tree, you always remember when you're creating a tree, that's a regression tree, you always split a region R0 to region R1 and R2, right, by choosing a split coordinate and a split threshold, right? So do that, but when you're picking this J, the first argument, this J is for you pick x1 to xp. So there are p choices that you can have for j, right? Which dimensionality of my input variable should I pick? Right? You want to find the best j comma s pair when you're splitting a region into two parts, right? Now, what random forest? The change will be just that instead of x1 to xp, pick j from some m which is strictly less than p. Okay. In a sense, I'm not letting you so in a tree construction, I'm supposed to start with a region, break it into two parts. But when I have to break it into two parts, I have to make this decision of which coordinate and which split level, which split point, right, for a tree construction. But I'm saying that the choice of which coordinate, I'm going to restrict to some subset of all the coordinates that I can choose. Instead of p coordinates, I'll say p by 2, let's say. Right? So that's the idea of decorrelation, because every time I want to make a split, I'm only restricting my choices. So that means most likely I'll not be using the same variables in another tree construction, or even another tree construction. Another time, if I run the same thing, you may not make the same choice. So this m is arbitrary. Okay. That I should explicitly point out, because that's what's letting you make different trees by. Of course, different bootstrap samples also may get you different trees. That's why bagging is gonna have potentially different trees. But in addition to that, because you're choosing only a subset of coordinates over which you're gonna pick the best j, you may have very different split points. I mean, the split j that you used as, let's say, the second split in one tree is probably going to be very different from the j that you use in another tree. Okay. So if features are very different, then trees are, very hand-wave way, that's going to be uncorrelated. Okay, less correlated at random from some subset. Okay, some m variables chosen at random. So that's it. That's random forest. So in the notes there is some comparison of random forest with gradient trees, gradient boosted method, gradient boosted models with trees. So, but it shows that gradient boosting model performs better as a function of increasing number of trees, but it's okay. I mean, both are pretty good models. I mean, it's data dependent of what the actual model is, right? The whole point is here we're moving away from linear models because we don't think that the conditional expectation of y given x is linear and so on. So it all depends on the data distribution, which we don't know. Okay. Yeah.
So you want to ultimately reduce correlation because you want to make separate trees that aren't kind of are biasing the results by being correlated with one another?
If trees are correlated, then we didn't talk about trees themselves, but we saw in random variables, if random variables are correlated, then there's you can't really reduce the variance of random variables. And why do we care about variance of random variables, right? It's expectation of whether things are correlated or not. Expectation is always the same. I didn't write it here, case dependent. Even if random variables are dependent, expectation of sum of random variables is still the sum of the expectation of random variables. Okay. Now variance, we said maybe a couple of terms go to 0 as b increases, but this term doesn't decrease because that's the term which is also capturing the correlation aspect. For random variables, we don't really care, but if you remember, in bias variance trade-off, we had this, the total expected square prediction error, for example, was the sum of a bias square term plus a variance term, right? EP was essentially a bias square term plus variance term. That's why we want to look at both, that's why we want to look at both expectation and variance. The first term is indifferent, whether indifferent whether things are dependent or not. Okay, it's the same expectation. So first term is not changing. The second term includes a variance of the predictor, but here we're saying that by this analogy, variance of dependent random variables doesn't decrease. It's related with correlation. So I want to kind of reduce the correlation. reduce the correlation may help me control variance. Ideally, I want to decrease the variance, but it's not clear whether it will actually decrease the variance, because I'm now choosing. I'm actually choosing m less than p m less than p variables to choose from for j. So I may be increasing variance. So it's not clear. Okay, but at least I'm decreasing correlation, and because there is a correlation which is over here. So ideally, in the best case, I do want to decrease variance, right? For the same mean square, for the same expected square prediction error, bias term is the same. Variance decreases, then it's good. Okay. And and what is the use of bagging over a single tree? Is that again, bagging over a single tree is also very similar logic. Okay. A single tree, expectation of a single tree, the bias of the single tree will be the same as the bagging bias, because you just saw that let's say all the random variables have the same mean, then expectation of an average random variable is also mu. So expectation of single random variable is also mu. So the bias term kind of remains the same. But doing bagging, as you saw, if things are not correlated, is really good, decreases variance. And things are correlated, it does decrease variance in the sense this number row, where is it? This number row is actually going to be less than 1. Okay. This number row itself is called the correlation. I've been using covariance. Correlation is like a normalized version. Somehow things push the numbers less between 0 to 1. Sorry, between -1 to 1 essentially.
Is it the correlation coefficient?
Yeah, it's the same thing. Correlation coefficient or correlation. Correlation between two random variables is just the covariance divided by the variance of divided by the square root of the variance of the first random variable and second random variable. So it just turns out that you divide this by sigma square essentially. And I just told you that this thing was rho times sigma square, and I divide by sigma square. So this thing is the correlation is rho. Okay.
Sometimes our model can perform better when using values than compared to others.
Yeah, it can. I mean, that is any model can perform better than any other model. It just depends on the true underlying. If you can tell me what the distribution is, we can probably try to derive whether one's model is better than the other. Okay.
So to build on that, if we had data that a lot of correlated variables, then of course we expect it to be better than bagging, and vice versa. Like if there's a bunch of uncorrelated variables, bagging might be better.
Uncorrelated variables. So here I'm talking about. So although this example was only talking about random variables, these are not your feature input variables. When I was creating trees, I was talking about correlation between these tree models. Okay, because bias variance trade-off is all about model variance and model bias. Okay, which can be evaluated at a single point. So bagging is just, you may have correlated trees. So in the sense, a consequence of that is that the predictions will be correlated. Okay, there may be different trees because the bootstrap sample may be different, so you can get different trees, but the trees predictions will be correlated. Okay, you're just trying to ensure the trees predictions are less correlated. It's essentially the same thing as saying you're trying to make the trees a little bit uncorrelated. But does that partially answer your question? So your question was about input variables. Input variables being highly correlated doesn't mean anything with respect to these guys. At least I don't know. Yeah. All of the models will have, let's say, p input features.
All of the models will have p input features.
Yeah.
Pi is the most important feature in that p variable. So each and every tree in Diamond would have pi as the first breaking node.
It may, yeah.
So that's the reason why each and every trees are getting correlated in a bag node. And in random forest, we are using the subset where the pi comes in different sets, so that each and every tree gets to be correlated.
Potentially, yeah. Okay, let's take a quick break, 5 minutes to 7 minutes, and let's resume. Okay, so let's resume. Okay, so now I'm gonna introduce a technique, just because it's a nonlinear technique actually. It's gonna be specific to regression, but just gives you a flavor of very creative ways that people created these nonlinear functions. So it's gonna be called MARS, multivariate adaptive regression spines, and the biggest takeaway, if you don't understand the nitty-gritties of how those functions, the nonlinear functions were created, it's going to be that how to create yet another additive model. So ultimately, the idea is to again get some sort of model, which is essentially beta I times bi of x. Okay, I is equal to 1 to m as your prediction function. Right, it's basically the design of these BIs. Okay, they are not linear. That's the kind of aspect that we are seeing in all of these things. And in particular for Mars, we're going to look at we're going to creatively design these BIs in a adaptive way, as in sequential way. Adaptive for us will just mean sequential. Okay, one after the other. And it turns out that these BIs will depend on previous functions that were added. Okay, here in some of the other models, there's no. I mean, you create a tree, you don't look at what tree you created before. Okay, essentially here there's explicitly you kind of see what functions are already kind of considered in the previous m-1 cases, and then the next model that you add, next function that you add depends on what you added before. Okay? That's the slight difference. Actually. That. Okay, let me finish this and just remind me that I need to talk about variable importance. Although some of you must have seen variable importance stuff in 572, right? There's not much of a any deep thought there. Variable importance is just saying I have a tree, maybe I have random forest, or I have a single decision tree. Maybe let's say regression, just to keep things simple. All it's saying is how many different nodes did I use the same variable as a split variable. Okay, so roughly I want a measure of, okay, if I've used this variable many times to split, then it's probably very important. Okay, that's roughly the idea behind variable importance. Okay, maybe a variable was used many times, but when it was used many times, was there a big jump in the least squares value in the region R0? And the two new regions I got, what was the the least squares, some of the least squares values in the new regions? Okay, how big was the jump? If the jumps were bigger for a particular variable, that variable is important. Okay, so the details are there in the notes. It's fairly standard fairly easy to kind of interpret. So if I have time, I'll come back to that. But I want to get to SVMs and some of the nitty-gritties of SVM, and also Mars. Okay. So first thing, let's come back to our data. We kind of missed this particular object for several lectures now. This is going to be, let's say x1, x11 to x1p, all the way to xn1 to xnp. Okay, it's n cross p dimensional matrix. Here now I explicitly have indexed the second coordinate as well. So let's say this is our data matrix. Then I'm going to create a bunch of functions. I'm going to denote it using the set C. The functions are going to be x. Let me just call this x1 minus x I1 plus x1 minus x xi1 minus x1 plus. So there are going to be n functions like this, there are going to be n functions like this, and so on. So okay, so I just wrote some expression. I'm going to kind of elaborate a little bit on that. So I'm saying that I have this data matrix. How many numbers are there? N times p numbers, right? These are numbers, let's say. And what I'm going to do is I'm going to create a function. So the function is going to be, let me call this function g. So the function, example function, let's call this g. So it's going to be a function of my input variable, not data, it's just an input variable. And then specifically, for example, I can say the function is going to be x1 minus x32, x1 minus x31 plus. Okay, what does this mean? So this is a function of all variables which only depends on the first variable, okay, capital X1. And in particular, the function is going to be like this. If, let's say this is capital X1, maybe there's a x31 value, which is a number. Then this function is saying if x1 is smaller than x31, it's 0. And if x1 is greater than x31, it's going to be just the value of x1 itself. I mean, the difference between them, and it's going to be positive. Okay, so it's like an offset function where, let's say x31 is like 5. Okay, all this is saying is that if x1 is less than 5, and it's 0. Okay, this function, because if x1 is less than 5, let's say this is 4. I know this is 5. Okay, let's assume this number is 5. Let's say this is 4. 4 minus 5 minus 1. I want to find the positive part of minus 1. There is no positive part. Let's ignore it. Okay. And another way to write this function is, which maybe even simpler, is just the max of 0, x1 minus x31. Okay, they're the same thing. It's just saying that if this number is negative, my function evaluates 0. If this number is positive, then the number evaluates to exactly an offset version of x1. Offset is exactly 5. So if x1 is 6, then 6 minus 1, 5. 5 would be the value here. 6 minus 1 will be the value. So these are piecewise linear functions. Piecewise linear just means on this piece it's linear, it's exactly function 0 line. On this side also it's a linear function. So it's a piecewise linear function. Okay. But let me just write it piecewise. And the opposite of that would be, let's say I had, because I'm adding functions of the form x1 minus xi1. So I just wrote it as short form. Just think of it as x1 minus x11, x1 minus x21, x1 minus x31, and there are n such functions of this form, right? For every different guy here, there are n such functions which are flipped. Okay, the flipped ones is essentially the same thing. Let's say x31 is equal to 5, then the flipped function will be same thing. It's 5. It will be like this. Okay, the slope here is 1. Okay, I mean, if you really want to think about it in terms of slopes and so on. The second function is just saying, if you flip this, write the function, it's going to be, let's say, it's a g prime of x is 5 minus x1 plus. So all it's saying is x1 is smaller than 5, then it's positive. And if x1 is bigger than 5, then this number is negative, so I'm only going to take zeros. These are called, these are a basic example of what are called spline functions. There are many other spline functions. So all I've done so far is say, okay, I'm going to play with these kind of piecewise linear functions. Okay, things which, in fact, just specific simple spline functions. Okay, I have NP of them. I'm going to play around with them to create my these BI functions, which are going to be my functions in my additive model. I'm always thinking of additive models. I want to find BIs. I'm gonna create BIs using these types of functions. Okay, and we're only looking at regression. So multivariate because we have 3 dimensions. Adaptive because I'm gonna keep adding one or two functions at a time. And regression because there's a regression setting. Okay, and splines because these are piecewise linear functions. Okay, data dependent functions. I mean, these are not in terms of splines, these are not the only functions. There's a whole subset of spline functions and so on. Let's not worry about it. For us, these are the functions we want to play with to create that particular additive model. Okay. Why are we doing this? Is Yeah. So there is you'll do it by p, all the p variables. So there will be n times p. So for each, actually, 2n times p. Sorry, 2n times p. Good point. So for each number, there's going to be 2 functions. This function and something like this function. Yeah. So 2n times p functions. Okay. Okay. So why these functions and what would b's look like? So b's, so bi of x will be just some sort of multiples of these functions. Okay, multiples sounds fine. Yeah, I'm just saying that you multiply these functions. Okay, and why do I want to create bi functions which look like multiples of these functions? It's just so that when you multiply these types of functions, they tend to be non-zero in small regions of the space. Output space. So in a sense, okay, let me give you a diagram. So let's say there was a function. So in terms of top view, okay, maybe picture. So top view. It's not one line. So let's say one of the functions is has this let's say one of the functions is x1 minus 5 plus, the other function is x2 minus 3 plus. Okay, if I multiply these two functions, it's basically something like let's say 5 comma 0, and this is 0 comma 3. Okay, it's only in this region that the let's say there's a b function which is like product of these two, then only in this region the function is going to be positive. In these regions, because of the nature of these functions, these regions it's going to be 0. Okay, so you're basically creating a nonlinear function which is flat as in zeros everywhere else, but it is like a positive, like a upward going function from this point onwards. Okay. Right. Actually, did I draw the picture correctly? I mean, 3 dimensions actually, yeah. 3 dimensions, okay. Yeah. So this is an example of a nonlinear function. That's why this is a nonlinear model, and we're gonna create functions of this form, like so that we capture. Maybe our output variable is taking some high values. So let's say we are in regression, right? So maybe in some region of the input space, you're supposed to, let's say I'm predicting income. Maybe in some spot of the region space, it's, there's, maybe there's an arbitrary shift and there's a higher income set. Then you kind of can capture that using these types of functions, and not just, this is going to infinity. Maybe there's 2 other functions which also multiply, and you kind of zoom into one region and make that non-zero. essentially. Okay. So this is what we're going to do, and given this intuition, the model is quite a little bit hairy, but let's not worry about too much of the intrinsics of the model. I'll give you the description of how you add these functions. So what you'll do is so you'll have two sets. I mean, set C was anyway there. There was 2 times n times p functions there, right? In the set C that I described earlier. In the set M, initially there's going to be one function, which is going to be whatever be the x, the output is always 1. So it's I'm just going to call that the one function. It's not really a function, it's just constant. Okay. Maybe I can just call it h naught. Okay. Let's call it h naught of x. It's just all ones. Okay. Constant. So what we'll keep doing is we'll try to add functions in a sequence. So for some m, right, I want to add the mth function. Okay. Actually, let me use the same notation in the notes. I want to use, so the way I'm going to add functions is 2 at a time actually. So I'm going to add function m plus 1 and function m plus 2. Okay. So let's say the number of functions here is right now 1. In this case, I'm going to add, I'm indexing function from 0, so I'm going to add the first and the second function. Okay. And the way I'm going to add it is to look at all functions of the form beta m plus 1 times, I'm going to look at functions of the form 1 times every other function. So 1 times a function here, which could be xj minus some number t, okay, arbitrary number t, or I could have used some constant c, I guess, c plus beta m plus 2 times 1 times x c minus xj plus. So I'm always going to pick functions in pairs. So I mean, if I have this function, I'll also pick this function. Okay, I'm going to try to. So initially I said I've already. So this set M will be the set of all the functions I've already picked. Okay. Currently, let's say I've only picked a constant function, just to kind of give you an idea of what's happening. Here, this set is always fixed, right? I mean, all these piecewise upward going functions, right? Those are 2 NP number. They're pairs. For every point in my data matrix, there's going to be 2 functions, right? Now, what I'm going to do is the first step, since there's only one function, I'm going to look at the possibility of this function times every function here. The possibility there are NP guys here. I'm going to look at this times this times this, and try to find that j for which this number is the best predictor for the bias. Okay. So what I'm going to do is I'll have the h naught of x. So this is a function, right? And I want to try to ensure that this is close to y. Okay. So find this pair of functions. I have many of them, right? I have NP of them. I mean, which j and which offset I'm not told you. So there are NP such choices. I'll find these guys such that this whole guy kind of approximately predicts y. Okay. I mean, that you can just minimize by minimizing least squares. Maybe you have to solve n times p least squares problems, but I'm just saying that find betas such that this predicts this. Okay. That's a regular regression problem. I already fixed the function, so all you need to find is the coefficients. Okay. Now let's say I did this and I figured out that maybe this function x minus x let's say x fifth variable minus x 57 plus and x5, what is the opposite one? X, actually this function should also have a coefficient beta naught, let's say. So I'll find this. So find this just means find these three coefficients, okay? I mean find the function pair, find the function, and for each function you'll have a beta coefficient which will make a prediction. And so you find the best function, which means that the best function will also have some beta coefficients. Okay. So let's say we found a function which is x5 minus x57 and x57 minus x57 minus x5 plus. So all this means is that the function that best predicts y is the fifth variable subtracted with the fifth observation. Oh, okay, it's not 57. It should be 7, 5 or something like that. Okay, let's call this. So my second index was always, let's say, second index was the index of the variable. So third observation, fifth column. Okay. So let's say this happened to be these two pairs of functions. So what I'll do is, in the set M, I'm going to put these two guys. Okay. Here there will be a H1 and a H2. Okay. This will be these two guys. Okay. Now I have these two guys on the left side, right? I've added two functions. Now I need to add the third and the fourth function. Okay. So what would the third and fourth functions be? I'm going to look at, because there's one, I'm going to look at all the possible functions here. So my general strategy is to look at functions which are products of this sign, that's all. So because I have one, I'm going to look at by default these functions themselves, which are the single shifting functions. But there are also these other guys. I'll also look at this times this as a possible candidate for my next beta n plus 1 and next beta n plus 2. That's all. So what I'm saying is, instead of 1, just think of h1 as also a possible candidate. h1 times something is also a possible candidate, and h1 times some other thing is also a possible candidate. So it's kind of increasing in the number of values you can have, but roughly the strategy is just this. I maintain a set of functions on this side. I have a set of what are called basis functions essentially, because they don't change. I mean, these are my most basic candidate functions. I'll always look at products of them. My starting point was because I did not have a thing on the left hand side, I just put ones there. But later on, I can consider functions where the previous functions that I've chosen, I'll put them there, put it here instead of 1, and look at those product functions which minimize, again, which kind of predict y in terms of, let's say, least square error. Okay. And then if I find any, let's say, pair of functions which minimizes that, then that product will be now added as h3, h4. So I'm adding my, so this was, so these are, the ones on this side are my added functions in my additive model. So they could involve products. That's it. That's the construction procedure. There's really not much insight with them. The insight was actually just what I said earlier with the with this type of region, that because these functions, if you multiply these functions, they kind of it's like an AND type of a function. So they kind of figure out a region and ensure that only that region is non-zero. So they can really capture non-linearities in the prediction. Okay, on the y side. Okay. Any questions about this? Beta n plus 1, beta n plus 2, you just do regression there actually. So you have all these choices, but given the choice, you have to just do, let's say, least square loss, find the betas. I mean, your objective is not to find, you will find the betas at the end. Let's say you already chose m functions, then you can find betas once you've already chosen the functions. Here we are just saying to pick the functions for each choice that you have, do a regression and figure out whether the regression has the lowest value, then you will choose those functions. There? H0 is by default, let's say you already have this function. Yeah. So I'm saying you always look at products of this side to this side as a candidate. So right now there was products of, let's say, since there was only one function, this times every function here. That's why I included you know, this and its cousin, I guess. And here I'll only have how many choices? NP choices. Like I can change these NP times, and out of NP guys, one of the guys will have the lowest least square error. Okay, that's the guy. Let's say that's this guy, x5 minus x35. Let's say. Then these two functions are going to be added into my this side, and then the next iteration, when I need to add two more functions, let's say, then I'm going to consider products of this times this guy, product of this times everybody else, product of this times everybody else. Okay, instead of one, replace the previously chosen function that you're not optimizing for. Then you'll have product functions also that you can consider as candidates which will minimize your least squares loss. And if there exists one product function which minimizes that least square loss, then you add it on to this side. So you kind of increase. You can get products because you're looking at products.
So when do we know when to stop planning processes? When you stop planning reductions in least squares?
Yeah. I mean, but the stopping procedure is not well. I mean, maybe there is some, but the best thing, of course, to do is to cross-validate and yeah. I mean, even in random forest, for example, how do you choose m, m less than p, and how many trees to add? Those are cross-validation based questions. Yeah. Yeah.
They are also in the form of that H1 and H2, right?
Yeah, they are in the form of they are in the form of H1 and H2 in this case. But next time they are these guys, right? Yeah, they are these guys.
Yeah.
But H1 and H2 need not always be in this form. H1 and H2 maybe in the next iteration maybe a product term.
Oh, okay.
This side is always fixed. These are the NP function or two NP functions that I have, pairs of functions that I always have. It seems to work well, not pre-deep learning era, so it was working well. So that's why I included this as yet another nonlinear model, just to kind of give you an idea that the world is not just random forest, SVM, and gradient boosting machines or gradient boosted trees. There are other models that you can also think of. You just want to capture nonlinearity in some way, some very in this creative way. It need not be the best one. You can also create nonlinear models as long as you can capture properties like this guy was capturing that in some small region they were able to ensure that there is non-zeroness. Yeah, right. Okay, so with that, let's go into support vector machines actually, or support vector classifiers actually. So my distinction between support vector machines and support vector classifiers is machines, I reserve the word for nonlinear methods. It's a nonlinear version of support vector machine in a sense. So now I'm actually going to look at again a linear model. But the nonlinear version is when I'll call it a support vector machine. Okay, the nonlinear version would be something when you add a kernel trick into it or do something else. We'll see what the linear version is, and then it'll become clear what the nonlinear version could be. Okay. Okay, so I have already polled many people that you've already seen SVM. So what do you know about SVMs? Maybe just a linear version. Linear just means if you think of kernels, just think of a linear kernel.
We're just trying to find the separation of the classifiers and then define that separation by only support vectors.
Yeah.
The boundaries
Yeah.
there.
So support vector classifier, we are in a classification setting, and on top of that, let's think of two-class classification setting. Okay. The two-class classification setting, there's going to be an interpretation in terms of, the model is such that, of course, the classifier has to separate two classes, right? Using some decision boundary. If the classifier happens to be a linear classifier, as typically then that name is given to those classifiers which will give a linear decision boundary. Okay, so you'll see that the support vector classifier is going to be a linear classifier. The decision boundary is going to be linear. Now there's this notion of support vectors that requires a little bit more nuance, or a little bit more explanation needed to what does it mean, what do support vectors mean. So support vectors, I think I'll try to explain support vectors after I describe a geometric intuition of what the model would want to do, and then I'll define what support vectors are. Okay, I mean I'll describe what support vectors are, because we need a notion of a hyperplane and a notion of margin and so on. So I'll first describe them, and then we'll get to support vectors. Okay, but what Scott responded is some of you who have already seen this. How many weeks ago did you see support vector machines? Some of you. Last year, last term. Or anybody simultaneously taking 575 and 572? You've seen it last week. Okay, so why are you guys not answering? Okay. Okay, so let's get into this. Let's see. Yeah. So let's say I'm going to use y's or g's. Oh, I'm using y's. Okay, for this section, let's use y's to be representing the class. So we'll use yi, and it could take two values. So let's say for the ith example, we have xi, yi, but yi can take two values, +1 and -1. Specifically, we want to fix this to be +1 and -1, not 0, 1, not 5, 10 or whatever. The class labels are going to be +1 and -1. Okay, and there'll be whatever n examples of these guys, right? N examples. And pictorially, you'll have a bunch of -1s on one side, and maybe +1s on another side. +1s. I'm just drawing the class labels, but it's basically, let's think of it as a two-dimensional, data set. So I'm just putting the labels at the places where the features themselves are. Right, the feature is two-dimensional, so it will be a point on that plane, and on the plane I'm just putting a -1, let's say. I mean -1 or +1, wherever they are. And let's, for now, let's think of a separable instance, by which I just mean that the classes are well separated. Okay, just for simplicity, let's say. It's happened. It may not, typically will not happen in reality. But let's say there are two classes which are separated in the sense of you can probably put a line between them in this case. And I also want to define another quantity which I'll call a hyperplane. Okay. Hyperplane is nothing but a bunch of points such that they're parameterized by, let's say, something. In this case, I'll use the parameter beta. So beta transpose x plus beta naught is equal to 0. Okay, this is a hyperplane. We have seen it in linear methods actually. Hyperplanes are just lines. Okay. So for example, just an example, just to refresh memory. So let's say we have a line like this, which is going through. It's going through 0, 1 here and 1, 0 here. What do you think this equation for this hyperplane, this in this two-dimensional is just a line? What do you think the equation of the line is? Y is equal to -x plus 1. Yes. Yeah. So the way, since I'm using x1 and x2, I'm not going to use y. I'm going to use x2 is equal to minus x1 plus 1. Okay. Or basically x2 plus x1 is equal to, or minus 1 is equal to 0. So you can see that this would be 1 times x2 plus 1 times x1, that would be beta, and plus beta naught would be -1 is equal to 0. It's basically x plus y is equal to constant. Okay. Since I introduced an hyperplane, I also want to introduce the notion of how far is any point from a hyperplane. Okay. So let's say I drew a line here. Sorry, a hyperplane here. I mean, in this two-dimensional anyway, a line. It need not be this way. It can be any orientation. And let's say I pick a point here. Okay. Let's say this point is x. I'm using x there. Okay. Here I'm using x as a general point. Here, let's say it's a specific point. I want to use x tilde. Is it tilde? Whatever, x bar. Okay. Use the point x bar. So actually, maybe I should just instead of x's here, let me put points p. Point such that b transpose p plus beta transpose p plus beta naught is equal to 0. Just so that there is no confusion. Okay. Now let's say this point is x. I want to find the distance of this point to this line or a plane in terms of Euclidean distance. Okay. Or yeah. So there's this. What is the best way to draw this? There's this. So you can actually think of these in terms of vectors. Okay. So there's an x vector. There's this perpendicular vector, and there's a perpendicular vector to the line or the plane, right? Let's call this. So this actually this vector is going to be just a beta vector. Okay. Beta. I mean, these two directions, these darker lines are the same direction. So beta vector is just saying what is the normal to the hyperplane. Okay. So yeah, what is the normal to the hyperplane? Okay. Now let's say this distance is gamma. Okay. Just I don't know the distance. Let's call it gamma. Okay. So, and let's say this point P here is actually, let's call it P, because all my P's fall on the hyperplane, right? I mean, in general, all my P points fall on the line. They are exactly on this line. I have a point outside it. I just want to, I mean, if I kind of look at the distance of that point to the hyperplane, typically, intuition wise, it's going to be like the distance is going to be what is the closest point on this line. That's let's call that P. Okay, and then the distance is going to be just the difference of these two vectors essentially. Then you can just see that since gamma is in the direction of x, gamma is this magnitude or the distance, right? And beta is the vector. So actually it's a vector here, but I'm just saying that it's a vector which is normal to this line, normal as in perpendicular to this line or hyperplane. Then we can actually just say that this p vector, let me actually put these as vectors, so just so that everything is clear. These are vectors. And the p vector is just going to be x vector minus gamma times beta vector divided by the 2 norm of b. So sorry, beta. So what is 2 norm of beta? Is just the sum of squares, square root of I guess beta 1 square plus beta 2 square plus all the way to beta p square. Okay. I mean, norm is just a short form for saying square root of the sum of the squares of the individual coordinates, and you've seen this before. Okay, when we looked at ridge regression, you've seen it. Okay, and why is this true? I said, this vector is vector addition basically. There's a vector p, so to really think of vector, it's actually a vector. You could put an arrow here, and this is a p vector. and you have a x vector, and there's another vector which is of length gamma, whose unit vector, whose direction is the same as beta. Beta may not be exactly unit vector, so I'm just dividing the beta by this guy. I'm saying that p plus this guy is equal to x, or if I subtract from x this vector, I'll get this vector. Same thing. So it's just vector addition. Is that clear? So if you have three vectors, okay, some vector, some vector, some vector, something like this, then you can say x vector plus y vector is equal to the third vector. This is vectors. Vectors and points are essentially the same thing. Vectors, just think of vectors as being this minus, this. Vectors are in terms of origin, so let's shift the origin there. Let's think of something like this. Is this clear? So I know the relation between the point on the hyperplane, a point outside the hyperplane, and let's say if it's gamma far away from this hyperplane, then this is the relation between the points, between the 2 points p and x, right? Okay. Now the reason why I wanted to bring in a hyperplane and the notion of a distance from a hyperplane, that's what I did here, is to say, okay, let's say I have a separable instance, which means that my positive class of examples is on one side, negative class of examples on the other side in this picture, right? I'm going to put a hyperplane between them. That's what I want to do, okay? Because I want to look for a linear model, and linear model essentially should always have a linear decision boundary, okay? So I'm going to put a hyperplane between them. So the picture is going to be negatives, I guess. I'm just going to positives. I'm going to put a hyperplane, right? So let's say this guy is actually that, the thing which is beta transpose p plus beta naught is equal to 0, okay? P such that this is true. All the points which agree with this equality, right? That's the line. And I want to look at distance of each of my training example points, okay? So there's this point here, maybe this distance, point here, this distance, maybe there's a negative sign here, this distance, and so on. All of them. Although I've only shown 4 on this side. Honestly, on the other side also I want to have distances, okay? And why do I want distances? Because if instance is separable, as in the two classes are, I can put a decision boundary between them and have no error, at least on training data, then it's not clear which hyperplane I need to pick, right? I could have picked this hyperplane. I could have picked something which is like a little bit above it. It would still be, separating the two classes on the training data, 0 error, right? But I don't know which one to pick. So to break that tie, I'm going to use this notion of distance from the hyperplane. So I know the distance of every point on the positive side, every point on the negative side from any given hyperplane, right? And so what I'll try to do is let's pick a candidate hyperplane and get some hyperplane, and let's say the nearest negative point is here, nearest positive point is here, okay? I'm gonna try to kind of visually think of a band, okay, between nearest to this guy, so nearest points to any candidate hyperplane. I can think of that as like a band, because those are the nearest points. All of the points are further away from it for now, right? So this band, I'm gonna call it okay, not this band, but let's say the negative point is closest to the, okay, in this picture actually both seem very close to each other. Let's say it's positive here. Yeah, this is the distance. They need not be equidistant from the hyperplane. There's a hyperplane, there are 2 points, closest points, and I'm going to think of a band as the band decided by the closest point in the picture. So maybe the negative is the closest to the hyperplane, so I'm thinking of the band as like the distance of the negative point to the hyperplane on each side. Okay, some shaded, maybe the shaded region. This is negative point, this is the positive point. So this I'm going to call as margin. Okay, the margin, which is a property of the current candidate hyperplane. Okay, so if I keep changing hyperplanes, I'll have different margins, right? Because I had, when things were separable, I could choose different hyperplanes. They all have different margins. So what I'll do is try to write down an optimization problem where I can maximize margin. Okay, so let's call margin m. Let's call margin is equal to 2m, because it's twice the one-sided band. Okay, so maximize to m, which is the margin over, of course, I want to maximize the margin, and I want to pick the hyperplane. And what are the parameters of the hyperplane? It's going to be beta and beta naught, right? So I want to maximize the margin such that the closest point is at least m distance away. M is that one-sided band, right? So what would be the the closest point? So let's go back to this equation. I said this is the distance of any point from a hyperplane, which is there's a point on the hyperplane, there's a point on the outside, and these are beta was the parameter of the hyperplane. Okay, there's a beta naught as well, but beta naught doesn't come into the picture. Okay, in terms of distances. Actually, wait a second. Where is it? Yeah. At least in this equation, beta naught doesn't come in the picture. Now, I know that P satisfies P transpose beta plus beta naught is equal to 0. Right? What I'm trying to do now is I know the relation between a point outside the hyperplane. There may be corresponding. There's going to be a corresponding point on the hyperplane. I know maybe there's a distance of gamma. What I want to do is I don't know this. Right? Let's say x is given and I know betas. I don't know this, and I actually wanted to compute this. Now, because I don't know two different things, let me try to get rid of this guy. So, what is the property that this guy satisfies? The P satisfies that P is on the hyperplane, which means that it satisfies this equation. Right? P is on the hyperplane. So, P transpose beta plus beta naught is equal to 0, because all points on the hyperplane satisfy this. So, what I'll do is I'll substitute what I know. P I know in terms of the point I care about and the distance in that equation. Okay, so it'll give me x transpose beta minus gamma times beta transpose beta, right, divided by norm beta plus beta naught is equal to 0, right? I just substituted the point P into this, point P. I only care about a given point, so at least this equation is in terms of a given point, and the distance I still don't know. Okay, or at least it eliminates one of the guys. I have to find this projected point. I don't know what it is, so I eliminated it. Right? But the distance is gamma, so I just want to kind of reuse that. So let me just write it here. What was the thing that I've written above is just x transpose beta. Was it minus or plus? Okay, minus gamma. And you see, beta transpose beta is just denominator squared. Okay, beta transpose beta is just the square of the norm of beta. Beta transpose beta, remember, is the sum of the individual entry squared. Denominator is square root of the sum of the individual entry squared. So one cancellation happens. So let me write that right here. Absolute value of beta, the norm of beta plus beta naught is equal to 0. Okay. So what I want to do is just push the distance on one side. The gamma is what I don't know. for this given point x. So let me just do write x transpose beta plus beta naught is equal to gamma times the absolute value of beta. Right? I just pushed the one term on right side, or x transpose beta plus beta naught divided by absolute value of beta is equal to gamma. So at least I know that if I've been given an hyperplane with beta and beta naught as the parameters, and I want to know the distance of this any given point to that hyperplane, there's an exact expression. The distance is equal to x transpose beta plus beta naught divided by absolute value of beta. The betas are known because that's a part of the hyperplane. X is known because that's a given point. Tell me that that's the distance. Okay. So distance of any point is given by this gamma. Distance of any point. This is the equation for. This is the expression for what is its distance. Now I want to say, since the closest point is m distance away in my picture, right? I want to pick that hyperplane which is the highest margin from all the points. The closest point is m distance away, at least exactly m distance away. So I want to ensure that all points. So in particular, xi transpose beta divided by, I guess the whole divided by whatever, xi transpose beta plus beta naught divided by absolute value of beta 2 is at least m. Okay. I want to do this, but there's still an ambiguity. Which one is a positive class? Which one is a negative class? Like, I want to find distance, right? And beta is actually where is it? Yeah, so actually the distance is supposed to be, this is distance, right, gamma. So it's supposed to be the absolute value of this thing. This thing can evaluate to minus 5. And this is a vector, this is a vector, this is a number. This thing can evaluate to minus 5. Right? But so the distance definition is actually absolute value of this. In the sense that it's clear, right? Denominator is anyway positive. Numerator, you need to ensure that it's positive. Right? So you can just put an absolute value there, and that's fine. To get that, I'm going to multiply this left hand side with yi. Okay. This is just a choice, that because you'll see that if, let's say, the points on this side are giving me gammas to be negative, so points on this side are giving me gammas to be positive, then it's fine. But points on this side, if this side is giving me gammas as positive, this side you'll see that gammas will give me negative. So I'm just multiplying this with yi's, it's a minus 1. So that this whole thing is a positive. So that's actually a distance. So I want to ensure that for all points on the left side, or positive points or negative points, are at least m distance away. Okay, that's all. So this was just to ensure that this is the definition of a distance. Okay. Actually, the distance is equal to absolute value of transpose b plus beta naught divided by. So is this clear? So this is the first problem. Pretty much says pick that hyperplane such that I maximize the margin, as such that I prefer that hyperplane which is the farthest away from both classes in terms of margin. Okay. So at least now I've said, okay, out of all the hyperplanes that can have, I can choose, I'll pick this one, the one which maximizes this margin. Okay. Now there's still a bit of ambiguity, which is as follows, that this page is left, which is that let's say I multiply all the points by 2, all the, not points, but let's say I multiply all of my feature vectors with, multiply them by twice, 2 times the number. Okay, which means that I have, let's say x1 x2 was 5, 10. Now it's 10, 20, double. What happens to the margin? What happens to the distance? instead of let's say so originally my input space was something like this. All the all x1 and x2, all the points were between 0, 1, 0, between 0, 1. Okay. If I double all the points, I'll get things which are between 2, 0, 2, 2, and so on, right? Okay. I enlarge the space. The margin also will increase, right? Just think of distance. And everything got doubled, which is not something that you wanna you wanna kind of not have this ambiguity that if I double my data, I get a different margin, and so on. So for that, what we do, which essentially means that there is a little bit of a what is it called? Too many degrees of freedom, essentially. Okay. Or in other words, I don't want to have this think about the scaling business. So what I'm gonna do is restrict my margin to be actually equal to 1 by beta square. Okay. This is just so that the normal vector, I'm gonna ensure that somehow I'm gonna relate the margin m, the smallest, the margin m to beta vector, so that I don't have this scaling issue. Okay, now I'll not have the scaling issue because before if I double things, m would have doubled, but now m pretty much depends on just beta, so it's not going to double. Okay? M only depends on beta. In a sense, what I'm saying is, if you had, let's say, a margin of 0.5 units, I could always rescale my data and make the margin 1 unit. Okay. It's a little bit unsatisfactory, so I'm just saying I'll fix the margin to be exactly, which means that margin could be anything, is what I'm saying. By scaling data, I can get an arbitrary margin. So I'm going to set the margin to be something which I like. I'm going to set the margin to be equal to 1 by beta, absolute value of beta. Okay. And why this choice? Because this choice lets me reduce. If I make that choice, I'm going to eliminate one variable. So in this optimization, in this problem that I said, I have to find a beta and a beta naught and a margin. A hyperplane and a margin. By setting m to be equal to some function of these other guys, I'm removing one variable in this optimization. Right? And the specific choice of 1 by beta helps me get a nice optimization problem. Okay. I could have written some arbitrary, I could have written, instead of 1 by beta, I could have written just beta, just absolute value of the norm of beta. But then the problem just becomes hard to handle, so people don't call that a support vector classifier. The particular choice, they call it a support vector classifier. So we'll get there. So let's say I make this substitution. Okay. Then you can see that if I make the substitution, okay, let me make the substitution. So you'll have 2 by, 2 is just a constant, so it doesn't even touch any optimization. So let me just make it 1 by. Actually, 2 is important. Okay, we can leave 2 inside. Doesn't matter. 2 by norm of beta. So I want to maximize over beta and beta naught of some number like this. New problem. Okay, new problem. Such that yi times xi transpose beta plus beta naught is greater than or equal to 1, where I is equal to 1 to n. So that's because I substituted m is equal to 1 by beta square. So 1 by beta square gets cancelled. So essentially this is a problem now. Okay, new problem. New problem. Oh, this is 2. I wrote a 1 and then I made it a 2. Okay, so you have this problem. So I'm just trying to get to the basic thing that does this look like an SVM problem to you guys? Yeah. not yet. I mean, two more slight modifications, which is that a maximization of a function, in this case it's a okay. I don't like maximizing 1 by something, so I'm going to do minimization of beta 2 by 2. I just flipped the term, okay? So beta by beta. So these problems are not equivalent, by the way. I'm modifying things. I set an m equal to specifically, so I restricted the problem. Here I'm changing, instead of maximizing some function, I'm saying minimize the inverse of that function. It's not always equivalent. Some special cases they may be equivalent, but here I'm just really modifying things. Okay. This change is innocuous because you're saying I want to maximize the inverse. I can, if whatever beta I set, if that beta maximizes, if the beta is such that it maximizes 2 by absolute value of beta square, then also if you flip that beta will actually minimize a norm of beta square in this case. Okay. So I did this, change 1. I'll actually write change 1 and change 2. So I haven't written the constraints, same constraints here and maybe also here. Change 1, change 2 is going to be minimize beta or beta naught of absolute value of 2 norms square by 2. Okay, I'm going to just square the thing. Just for now, for us, we just want to understand this as modifications. There are some justified reasons for squaring, because otherwise I'll have square root something. It's okay. I mean, it's fine. Nobody will object to that. But this kind of gets rid of the square root in the definition. So in the objective, so it's nicer. Okay. So this maximization to minimization one change. I mean, there's already one change I did. I mean, there's already one m is equal to 1 by beta square I did. Then I flipped the objective, right? And then I squared the objective. Right? Like from here to here is actually very innocuous because this, turns out, I don't know if you've looked at any optimization problems, but this is called a convex function. Okay? Norm is a convex function. Like a ball is a convex function. If you minimize over the ball, you'll only have one optimum. Okay? Norm is also like a ball. 2 norm is exactly like a ball actually. And since it's a convex function, and x square is also a convex function, it's like a parabola. So you can always a convex function with a convex function kind of stays convex. So some stuff like that, but it doesn't matter. For us, it just changes. So this problem is called the support vector classifier. Okay, the classifier, the hyperplane, which minimizes the norm of beta, such that these conditions hold. These conditions, there are n such constraints, right? That's called a support vector classifier. That particular model is called a support vector classifier. It's not described in a analytic way, right? It's described in a computational way. Some model will minimize this, and that model is called support vector classifier. Okay. Any questions at this point before I move forward? So, those who did support vector machines, was this explained? So you should have told me that I don't have to spend much time on this, right? Okay, that's fine. So if it's too repetitive, then you should tell so that I can cover some new material. For others. That's fine.
It's just a lot clearer after going through tonight.
Yeah, that's fine. I'm just saying, particularly for you, don't worry about it. Others I know it's a heterogeneous composition. Yeah. Okay. Yeah. So now one more generalization, because right now actually there was one nagging or unsatisfactory assumption that I made, that the classes were separable. Okay, I was saying that there is a hyperplane which kind of splits positives and negatives, and therefore my margin kind of was very clear. There's going to be positive on the positive side. There will be a closest point. On the negative side, there will be a closest point. Whichever is the closest of the two, that's my margin, which is a number for that hyperplane. I want to get the best hyperplane. Okay. So I want to relax the separability restriction, okay, which essentially means that there's not going to be a hyperplane which can exactly put positives on one side and negatives on the other side. Whichever hyperplane I pick, there's always going to be some positives on one side and some positives on the other, some negatives on the other side, in the opposite sides. Okay. For example, let's say a simple example. Let's say there's a plus, 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 there's a minus, minus, minus. So there's no hyperplane which will kind of split this exactly, right? Besides that, pluses are on one side and minuses on the other side in this two-dimensional setting. You can try to play and find a hyperplane, but you will not. So basically, I want to kind of let some points fall on the other side of the margin. Okay. I'm okay with some points falling on the other side of the margin. Okay. How do I do that? So that is through the introduce slack variables. Variables just means that I had this original problem which only was minimizing over beta and beta naught, right? Those are my variables. I just need to find the beta and beta naught such that the subjective is minimized. So I'm going to introduce slack variables. So now these are additional variables. In fact, I'll have a slack variable which is going to be ci, which is I is equal to 1 to n. So if I have 100 data points, there will be 100 now variables. Too many variables now. I'm blowing it up. But ci is 1 per example. And it's basically saying if this particular example, really is messing up, like if I could push that example, if I'm willing to forget that example, then I'll get a, decent decent hyperplane. Then I am willing to allow for some slack for that variable. Like it can fall on the other side of the margin. Even if it's a positive class, it can fall on the negative side of the margin. Okay, so that's what it means to be slack. Give a slack to that example. And it's not like we a priori will choose which examples we'll choose to give a slack or not. That's why the slacks are variables. In the sense, let the problem decide, or let my optimization decide which example needs to get a slack, so that it can fall on the other side of the margin. Okay. And that's going to be this support vector classification, support vector classifier for the general case, non-separable case. It's going to be minimization over beta naught and ci of 1/2 of square. This was there as before, right? Then I'll say plus some constant times sum over I is equal to 1 to n of these ci's. Okay. So I want to minimize these slacks. In the sense, I never want to give any slacks. So these are like numbers, which ideally I want to set it to 0. So that's why I'm minimizing this objective. And I initially anyway had this objective, which is related to maximizing the margin, right? This I'm just adding as an additive term, saying that, okay, you try to find, the best margin hyperplane, but you have a slack budget, which is, not budget, but think of this as I can allocate slack for every example, but I want to, whatever I allocate, there should be as low as possible. Ideally, they should be 0. Okay. Minimize these two. Now, such that yi times xi transpose beta plus beta naught. Previously it was greater than or equal to 1, but I want to provide slack. So I'm willing to say it's greater than or equal to something like this. Okay. So they need not be that margin away. They can fall on the other side, which just means that the margin is going to be smaller. Sometimes it's going to be flipped. It can even be negative. So So I also want to ensure that these are slacks and these are positive numbers. Okay, these I don't want to set it to. I mean, ideally I want to set all these slacks to 0, which means that this is the previous problem that I just wrote. But I can't do that. I want to allow for some points to not fall on the majority class side. So I'm gonna give some slack here. Okay, and say ideally I don't want to give anything, but it's okay. I mean, I can give some. So that's the idea here. Okay, so this version solves the problem where I'm not assuming anything about the 2-class problem. So give me any 2-class classification problem. I can solve this problem maybe computationally and get you the support vector classifier. Okay. In fact, this is called the Primal support vector classifier formulation. So we are not done with the support vector machine story. Actually, it's just 1/2 or maybe 1/3 of it. Next class, we'll just a quick prelude of what's going to come next class. We'll look at something called the. So at this point, really, I haven't even told you what support vectors are. Okay, we haven't got into the justifying the name of the method. So next class we'll look at dual support vector classifier formulation. Okay. So we'll try to kind of understand what is meant by primal, what is meant by dual. So dual support vector classifier formulation will give us this notion of support vectors. Okay, and and they'll also allow us to do what is called apply kernel trick. Some of you may know what kernel trick is, but for others, don't worry about it. It's a way to make this linear 2-class classifier non-linear. Okay, and so support vectors. What are support vectors? It's essentially although I will write the dual formulation and then tell you what support vectors are. Here, in terms of pictures, a support vector is nothing but that data point, that example, for which the band, if you look at, I picked the hyperplane, it has a specific margin, right? Now, take the hyperplane, make a band around it. In fact, it's going to be a plane, so there's going to be 2 other planes. There'll be some points on each side which will touch it. Okay, some points which will touch it, because if they don't touch, I can expand the band. So there'll be some points on either side of majority class will touch it, and there'll also be some points which will be because of the slack business, there'll be some points which will be on opposite side. Okay, there's a huge positive positive examples on this side, maybe there's one positive on the other side of the hyperplane. Now the points which are touching the margin and the points on the other side are called support vectors. Okay, because they kind of justify the choice of this particular hyperplane. All other points are kind of not influencing anything about the choice of the hyperplane. And why is that? Intuitively, because when you're picking that hyperplane, we only care about the margin to the nearest point on both sides. So the nearest point is what's dictating, in some sense, which hyperplane to pick. The farther points on positive side and negative side, let's say, they don't really impact, whether they are further positive away or whether they are a little bit closer, doesn't influence anything. Okay, the nearest points, on the other hand, if they move a little bit, are going to influence the choice of the hyperplane quite a lot. So that's just a kind of a reason why they are called support vectors. Okay, it's not just the nearest points in the non-separable case, as in the points which are on the margin, but also points which are flipped, in the sense, because even if I change that, the slack budget changes, and therefore your hyperplane also choice may be suboptimal. So those are called support vectors. Everything else which are far away are not called support vectors. But we will see that through this what is it called, dual formulation next time. Okay, that's it.